So the title of this video is "A Rose by Any Other Name Would Smell as Sweet." So it's a quote from Shakespeare. What I want to discuss is how the beauty of abstraction, how it helps you to understand mathematical objects in an even better and clearer way. And so this is based on part of the book and going over the exact same ideas. And so the quote will be explained in a moment. So here's two examples of groups. Z mod 4z, so integers mod 4, under addition. So I should make that clear that this is the addition operation, not the multiplication. Here's the multiplication table, or I should say the addition table. On the other hand, look over here. Let's look at this geometric object. So it's a square with this little line segment added on to each of these corners. You can see that the only symmetries of this object are the rotations. So by adding these little notches, you see that the usual mirror symmetries of the square are no longer symmetries. For instance, the horizontal flip has the problem that this line segment would go down here sticking straight up, but that's not currently there. So the symmetry group of this figure, we see you've got each of the rotations. The identity rotation, the 90 degree, 180 degree, and 270. And it doesn't take long to notice that if I send I to row to the I get a bijection between these two sets, with the feature that the multiplication table actually matches. So you see here's a 3, here's row cubed. What I mean there is that if you look at this map, so let's call this map sigma. Sigma of I plus j turns out to be sigma of I times sigma of j. In other words, a rose by any other name would smell just as sweet. It doesn't matter if you're using congruence classes to denote this group or these rotation operations to denote this group. It's essentially the same group. Even though this came up from studying congruence relations on integers, and this came up from studying symmetries of a geometric object. So that's what they mean by the beauty of abstraction. You're seeing the same group or same structure arise in two different locations. And the notion of same is that you've got a bijection between the two sets that preserves the multiplication operation correctly. In particular, any problem you want to study involving this multiplication table, you could equivalently study using this multiplication table. And so this is the notion of isomorphism in group theory, that it doesn't matter how you choose to label your groups. If there's a bijection that preserves the group structure, either approach works. So the point is, these two groups are essentially considered what they are called isomorphic, and sigma is what is called an isomorphism. It's a structure-preserving bijection between the two sets. And there's actually a lot of areas of mathematics where, in two different areas of mathematics where people were studying groups, they end up looking at each other's notes and realize they're working with the same group, and then end up discovering the connection between their two branches of mathematics. So isomorphisms are actually quite useful for discovering relationships between even branches of mathematics. There's another example of isomorphism. It's worth pointing out, when I wrote down the matrices for the symmetry groups of the square, I used 2 by 2 matrices, but if you check the textbook, they actually use 3 by 3 matrices by working one dimension higher. And so somehow these are actually the same group, even though they were using a different set of matrices, because they were describing the exact same symmetries. And so the 2 by 2 matrix I had associated to, say, a horizontal reflection corresponded to a 3 by 3 matrix in their version of the story, and so there's a bijection there. In particular, the details don't matter whether you're using whether you're encoding the symmetry as a 3 by 3 matrix or 2 by 2 matrix. It's just the fact that if you do a vertical flip, a horizontal flip followed by a vertical flip, you're going to get a certain rotation. Another concept that will pop up soon, and already sort of popped up in that Galois video, is the notion of subgroup. A subgroup is a collection of a subset of a group that's also closed under multiplication, inversion, and identity. For instance, those rotations, the powers of the rotation operation, actually give you a well-defined subgroup of the symmetries of a square. And so we've seen this before. If I were to actually change the square with a rectangle, I get new symmetries, but those symmetries are really actually just a different subcollection of symmetries of a square. And so you can actually start, given an abstract group, you can start to actually look at its subgroups and try to determine the structure of its subgroups as a way to get more insight onto the structure of a group. Finally, the most broad perspective on this kind of concept of the importance of abstraction is the notion of a homomorphism. So isomorphism is essentially saying that, it turns out you and your friend down the street are both actually working with the same algebraic structure just by different names. This one is slightly different. It's saying that there's a function from G to H, where G and H here are groups, but the feature that for any two elements in your first group, when you multiply them together and then you apply this map, you actually get the same thing as if you apply the map to each of the elements and then multiply them together. And you require the identity of G to get mapped to the identity of H, and the inverse of an element in G to get mapped to the inverse of phi of A. So you've got some sort of function that's preserving all your multiplication structure. But it's not necessarily bijections. If it were a bijection, then you'd actually call this an isomorphism. And I will give at least a few examples of homomorphisms to get the idea of why they're important. The examples I give all actually come from lower level math courses. So here is actually the first example. It's the exponential map. It sends the real numbers to the positive real numbers by sending x to e to the x. And a property of exponents is that e to the x plus y is e to the x times e to the y. What that really means is that this map, called exponentiation, is a homomorphism from the real numbers under addition to the positive real numbers under multiplication. And so this is a short way to express a fact we normally teach, that exponentiation has this property. It also tells you that e to the 0 is 1, because 0 is the additive identity over here, and 1 is the multiplicative identity over here. It also tells us the other familiar property of exponentiation, which is that e to the negative x is 1 over e to the x. Because negative x is the inverse here, and the reciprocal is the inverse here. So this actually tells you that you've got a homomorphism between these two. It actually gives you the familiar properties of exponentiation. In fact, there's the fact that's hard to prove that this is actually a bijection, because you usually point out that the range of the exponential function is 0 to infinity. So you actually do get a bijection here. What is the inverse map called? It's called the natural log. Since this function has to be an isomorphism, that means that not only is this a homomorphism, it's an isomorphism, which means that the inverse also sends multiplication to addition. And what does that tell you? That tells you that the natural log of x times y is the sum of the natural logs. It also tells you that the natural log of 1 is 0. And that the natural log of 1 over x is negative natural log of x. So, a lot of the properties of logs actually come from this perspective. The only one that doesn't come from this perspective is the natural log of x to the y being y times the natural log of x. That one's actually a little more complicated and doesn't follow from these properties. It follows from another property of exponentiation that doesn't come from the group structure. And so we see a very common example from college algebra is actually an example of an isomorphism of two groups. As one other example of an actual homomorphism, consider the determinant map. So given a 2 by 2 matrix, the determinant is just the diagonal, product of the diagonals minus the product of the anti-diagonal entries. It's a theorem from linear algebra, and you can prove it directly if you want, that the determinant of the product of two matrices is the product of the determinants. In particular, this tells you that it sends multiplication to multiplication. Now, I said group homomorphism. One thing you notice immediately, if you're clever, is that 2 by 2 matrices in general do not form a group. Namely, if I take the example 0, 0, 0, 0, the inverse of that all zeros matrix actually does not exist. If you actually try to do any multiplication with this matrix by any other, you're going to get the all zeros matrix again. In particular, you're never going to be able to get the identity. So in fact, there is no inverse. So what does this have to do with groups? Well, whenever you have a function, a homomorphism from a monoid, so set with an associative multiplication, to a group, by the way, I should point out here, this isn't a group yet, but this tells us that what could you do? Well, let's look at the things that don't get mapped to 0. Determine it from some sort of subset of matrices that don't get mapped to 0. We note, of course, here that we need a name for this set. Let's call it GL2 for some mysterious reason. So these would be matrices with non-zero determinant. Now here we have a group. Well, then you can go back and look upstairs and see, well, do you have a group upstairs? And it turns out you can. In fact, that's a theorem from linear algebra. The inverse of a matrix exists if and only if the determinant's non-zero. This was the formula I already gave. So this is not a group homomorphism. But whenever you have a situation like this, it tells you how to create a group. Or actually to figure out which elements in your upstairs monoid are invertible by just looking at the things that are mapped to invertible elements here. And that's actually how this ends up happening in linear algebra. And so I throw away 0. Now I have an honest-to-goodness group. I look at these elements that inside M2R that actually map to this group, and I see and discover that these are exactly those matrices that are invertible. So now this is in fact a group, and now this is in fact a group homomorphism. It satisfies the property that sends product of matrices to, the determinant of the product of two matrices is the product of the determinants. And another fact we usually see in group theory then is that the determinant of the inverse of a matrix is the negative of the determinant. Right? Or is it? No. It's 1 over the determinant. And the determinant of the identity matrix happens to be 1, so it preserves all the group structure. This is definitely not an isomorphism because it's possible for two matrices to have the same determinant, so it is not injective, even down here. If I take, for instance, an example 1, 1, 0, 1, and the diagonal matrix, these two matrices both have determinant 1, but they're actually different matrices. So this is in general not injective. So it is a proper homomorphism. So you start to see homomorphisms from, or maps from other classes are actually examples of homomorphisms. And so any theorem about groups, or any theorem about subgroups, or any theorem about homomorphisms becomes theorems that tell you information about specific examples. Here I mentioned one more example of a homomorphism. Given congruence mod p, there's a nice map from z mod p to z mod p, given by taking an integer a and raising it to the pth power. So we've seen before that a plus b to the pth power is congruent to a to the p plus b to the p when you work mod p. And so in particular, that means that if you do the sum of these two congruence classes and then raise it to the pth power, and applying this definition, you get this summation. So this is, of course, the definition of sigma of A plus B. We see is the class of A plus B to the P. But according to our theorem, that's the class of A to the P plus B to the P. But by definition, that's A to the P plus, by definition, that ends up being sigma of A plus sigma of B. And so there's an example of a homomorphism that was introduced recently. This one's so famous in mathematics, they actually have a name for this. This is called the Frobenius map. It sends an element to its pth power in certain rings, and this is the prototypical example of a ring that you would do this in. And so it's a very important map in number theory, and it is an example of a homomorphism. In this case, it's kind of weird because it actually maps from the group to itself. Of course, one question that's hard is this actually a bijection? Well, that's an interesting question for a different day. But it is, in fact, a homomorphism at least.